Welcome to the Be Curious podcast, the podcast that champions solutions to some of the world's biggest problems. I'm your host, Louise Houghton, and in each episode, we get curious about a different subject, from the food that we eat and the clothes that we wear to overflowing landfills and ocean plastics. All of our guests have brilliant minds and innovative ideas to allow us to lead a more sustainable, conscious, and pollutant-free life. And the best part is, this podcast isn't just about listening. It's about building a community and connecting like-minded individuals who are curious about alternatives to enhance their lives and the longevity of the planet. And if you're curious already and you want to find out more about the wonderful gifts and services given to us by our many guests on the show, then just head over to our Instagram for more information. You can find out how to enter at BeCurious_podcast. It is such a pleasure to share what companies and organizations are doing for future generations. Everyone featured works in a sustainable way, and I love how much people are on the same page, wanting to create and innovate in order to make change. If you feel the same, then why not follow in my footsteps and sign the Science Declaration? This declaration is a call to all nations, societies, and organizations to devote more resources to the advancements of science and technology. They're encouraging people internationally to join forces in battling debilitating diseases, ensuring sufficient food for a growing world population, stopping the destruction of our environment, and engaging in joint endeavors to elucidate the secrets this fascinating universe holds. To add your name, go to make-science-not-war.org and take an active stand to demand more money is put into improving rather than destroying our world. You can also hear more about this declaration at the Future Insight Conference that's being held in Mainz, Germany on the 10th and 11th of July. Over the 2 days, academic and industry leaders will come together to share their knowledge and latest innovations. The conference focuses on interdisciplinary and transdisciplinary conversations and will cover topics of science, technology, and everything else making huge steps forward in their respective industries. You're also welcome to enter competitions and contribute to their Dream Board, a place that allows you to dream big and share your visions for the future, what you want to see invented, and why. It's really your chance to get involved and take an active role in leaving the planet in a better place than when you were born onto it. That's how I see it anyway, and I hope you share the same view. To check out the competitions, get tickets, or write out your dreams, head to curiousfutureinsight.org for more information. Today, we're getting curious about CO2 and discovering how one innovative scientist has found a way that we can use our planet's excess carbon emissions as fuel. Joining us for the conversation all the way from Europe is Professor Dr. Tobias Erb, Director of the Department of Biochemistry and Synthetic Metabolism at the Max Planck Institute for Terrestrial Microbiology in Marburg, Germany. Thank you so much for joining us, Toby.
Thank you for hosting me.
Of course. I'm excited to see you at the Future Insight Conference this year in Mainz, Germany. I just told our listeners about it. And what I also need to mention is that there is the option to join the conference virtually as well. So if you do want to do that, go to curiousfutureinsight.org and you'll find out how to register. Now, Toby, this will be your second time there at the conference. When is your talk scheduled for? Do you know?
Yeah, my talk is scheduled for Wednesday afternoon, directly after the award ceremony of the Future Insight Prize.
And the Future Insight Prize is the reason that you were there back in 2022, because you were awarded with the prize itself, which is a prize that was created by Merck Group KGaA to fund research for ambitious dream projects in the fields of health, nutrition, and energy. And with your award, you received €1 million for your research on converting CO2 to fuel. How did it feel to win that prize?
It felt great, of course. It was fantastic and completely unexpected news, at least for me. And I think was fantastic acknowledgement for the work of my team. And it's, of course, also a big motivation for us to keep on going and doing our research. And I have to say, of course, €1 million helps a lot, too, because it adds a lot of degrees of freedom to our research.
Sure must do. How long have you been working on your research?
I guess it's around about 15 years, and I started thinking about this project as a postdoc. I think we developed the first prototype within 5 to 7 years, 2016, I think, roundabout. And now we're at the stage where we're really trying to implement these solutions. And again, this sounds like a long time, 10, 15 years, But if you think about reinventing a process that has been built by evolution over billions of years, I think we're quite fast.
And what is the size of your team?
Okay, we are currently around about 40 scientists across all career stages, from the intern to the senior postdoc or senior scientist. And more importantly for me, also across all different disciplines, right? From biology to chemistry, physics, and even material sciences. And I think that is exactly the right mix of people that you need if you want to tackle a big challenge in an interdisciplinary fashion.
Yeah, and before we actually get into your research, I would love to just talk a bit more about CO2 emissions in general. Do you know what the average person's carbon footprint actually is?
Yeah, that's a very good question. So, of course, it depends strongly in where you live and how you live. And so let's just take an average German. I think we are around about 7 to 10 tons per person. And now you can look into different parts of the world. Let's say North American would maybe use 1.5 times more CO2 per capita, whereas somebody who lives in the global south would only have a fraction of it, maybe a quarter or a fifth of the CO2 emissions per person. So the lifestyle really is one of the most important factors.
And the lifestyle is, of course, because of everything that we do more so in the Western world, travel more and eat in excess and all those kinds of things. So, what about those kind of different industries? How do they contribute?
Yeah. So I think it might be even better to think in sectors, as you just mentioned. Let's think about transportation, which adds a lot to the CO2 emissions. Let's think about energy consumption, even using computers, using software, Chat GPT, right? It's a big thing too. And then, of course, meat or eating agriculture is also a big contributor to emissions. And last but not least, it's all the construction industry.
What kind of environmental impact are we going to see if we continue with these emissions and them increasing in the way that they have done over the last decade or so?
Yeah, I think this has been well established. I think we've all experienced that. It's actually since the roundabout 1950s when the Anthropocene started. I think we know that is an increasing global average temperature, which comes along with extreme weather conditions, flash floods, droughts, wildfires. And I mean, this is pretty clear that we need to deal with these excess CO2 in the atmosphere.
And it seems that governments are not necessarily doing all that they could as well. Why do you think that that is?
That's a very good question. I think first and foremost, it's probably really the lifestyle of us human beings, right? And I think this comes along with all the resources, traveling, housing, energy, as I just said. And the problem is that we typically are stuck with certain technologies, and these develop only very slowly. We are very convenient once we have a certain way of living, right? And to change all these behaviors, it's much more complicated, right? It's a bit like in biology with evolution. Once you fixed a certain trait, it's pretty hard to get into a new optimum, right? And radical new solutions. And it's actually this nice story when people talk about rockets, right? How the modern rockets were transported from A to B. Now this all goes back to the Roman Empire and the civilization of first chariots. So sometimes standards set by industry are just perpetuated over centuries. And I think that is the challenge, the way we do things.
It's not that the government have a vested interest in the oil and gas industry then?
Well, the oil and gas industry has made us rich, right? It has also led to, of course, improvement in life expectancy, right? In life quality. So there is something that is attached to using fossil fuels to produce new compounds. And the question is, how can we replace the way we do things, right? Not necessarily the product, but the way how we create the product. And I think this goes along with, on the one hand, trying to incentivize new approaches and to become also aware of the opportunities that lie in creating a sustainable future.
So, how do we get the governments to actually get on board and take responsibility and really promote renewable energy resources?
And it's two ways, right? One thing is to incentivize, right? So you can support or you can punish, right? You can tax CO2. And I think these are the both ways we have to find a way in between. And I'm not a politician, by the way, so I'm a scientist. And I think I have the freedom to think about the future. And governments can also be technology open and they can support science. And I think that is what I'm advocating for, right? I can develop future technologies. I can be curious about the world of tomorrow. And I think that's my biggest contribution. And then society and governments have to decide if they want to use the technologies. And I think this is how I would look at this interface and interplay between politicians, scientists, and the society.
What do you think that the biggest way to combat CO2 actually is that they could do?
Actually, look, this is too big of a problem that you would have one solution to it. And I think what we'll see is way different solutions. So transportation, I think electricity is key, right? You can look at agriculture, maybe swapping a bit out the meat consumption, lowering our meat consumption is one way to do it. And then there's also biology in the mix, which can actually fix and capture carbon. And I think that will be the contribution that we can do as biologists, using and empowering biology to become even more efficient at capturing the CO2 from the atmosphere.
Yeah, I think I agree with you. It needs to come from all different angles. And I love seeing initiatives from companies, even ones that just say, oh, they'll plant a tree if you buy something from them. There's even an Instagram account called Plant a Tree Organization. And just for following them on Instagram, they'll actually plant a tree, up to 100,000 trees, I believe. So even just small initiatives like that, seem to be helping in some way or another, but that's just on a smaller scale. We need to do something on a more global scale and on a much bigger scale, which is, I know, what you're doing yourself. So where did the idea for the CO2 to fuel converter come from?
It comes actually from my basic interest and curiosity how nature has found a way to capture CO2 from the atmosphere. It's something we cannot do as chemists. I'm a trained biologist and chemist. And as a chemist, I have only limited tools to capture atmospheric CO2. And biology can do it in a sustainable fashion. And this fascinated me. And then I started thinking about where the limitations of biology are and where maybe chemistry could help and blend in. And this is exactly when I started to think about how to use synthetic approaches to improve biological carbon capture.
And so what did you know about photosynthesis and the value of CO2 before you started? I mean,
Yeah.
we all learned about photosynthesis in school, but for people who might need a reminder, do you want to tell us?
Fantastic. So if you want to do it in one sentence, I think photosynthesis is a sustainable way to capture the greenhouse gas CO2 with light as energy source. And it's as simple as that, right? It's a plant, it's a filter that filters CO2 and makes biomass out of it. And we can eat the biomass or we can construct a chair or a house from this biomass. So that's a fantastic sustainable way to capture CO2. So what's not known is that nature has even invented other ways beyond this classical photosynthesis way. In fact, 7 other pathways. And this has inspired me to think, well, this is 7 solutions. There might be even 8, 9, 10, 11 solutions, or some of them nature has never thought of. And this is where the idea of synthetic biology and reinventing photosynthesis came.
Can you dive into that in a little bit more detail?
So, the overall motivation is to look how nature and the different ways of how nature can capture carbon dioxide from the atmosphere. And then we want to extract this principle and we want to think how to build it from scratch in a new way. And I want to give you a different picture for that. Think about how we humans learn to fly across the ocean. We studied birds and bird flight, and then we built a machine, a plane. A plane has wings, but the wings don't flap and the wings don't have feathers. So now go back to photosynthesis. You can use light to fix carbon dioxide. Nature does it with photosynthesis. Let's extract those principles and build a device, maybe a small biomachine that can do exactly the same, but much more efficient, and it can be constructed very differently. So that's basically the way I would look at our approach.
It's so interesting to hear about all of the developments that you've made within your research so far. And I know that you've named your research the catch cycle. Can you tell us a little bit more about where that name came from?
So the catch cycle is basically a new operating system for carbon capture. It's like the software that allows you to capture carbon in a biological software in a sense, right? And we called it catch because it stands for, oh man, crotonyl-CoA, ethylmalonyl-CoA, hydroxybutyryl-CoA pathway. That's an awful name. So we thought catch might be better. And you also play a little bit with the word of catching CO2 from the atmosphere.
It's not spelt like catch, is it? It's spelt, how do you spell it?
It's an E, it's a catch. I don't know what the English translation would be. In Germany, you would call it catch. So that's maybe my German roots in me. So, you want to give your operating system different names. So like you had Windows, right? You would have the iOS system, the DOS system. So we basically name those different cycles. We also have a HOPEC cycle, a theta cycle. So these are all different flavors and different solutions for the same problem that we currently prototype.
And what is the rate of carbon fixation from this bioengineered system compared to the natural form of photosynthesis?
Yeah, thank you. I would basically take 2 measures or 2 ways how to compare to natural photosynthesis. And there's 2 things that are important. First of all, how fast or how much CO2 can it capture per time? And so the catch cycle, for instance, uses a new enzyme, a new biocatalyst that can capture CO2 10 to 20 times faster than natural photosynthesis, which allows you to fix 10 to 20 times more CO2 in the same time. It's fantastic. So it's fast. And you also want to actually use little energy, right? Sunlight, hydrogen, electricity. And the question is, how much energy do you need? And so the catch cycle again beats natural photosynthesis, and needs half of the energy that natural photosynthesis would need. So in summary, it's a fast and very energy efficient solution to fix carbon dioxide. It's like a Porsche you drive with high speed and you just need a little bit of fuel to go along 100 miles, 200 miles. So that's basically the way we look at things.
And just to, I know you've been doing these analogies, which are brilliant to bring it into a more understandable form for everybody listening. But just so I can clarify then, what we're really sort of looking at here with this catch cycle is photosynthesis that you've taken down. You see all these different pathways, and then you've seen that these different pathways create a way, and you can actually bioengineer them to make them without using the actual plant.
Yes, that's correct. So we basically operate the whole system outside of the plant. That's fantastic. That's basic science. And we can prototype it much faster. Think about how long it takes to grow a plant, to test its effects. So the idea really is to extract this principle, to build a new operating system, and then bring it back into, for instance, a plant or another natural cell or even artificial cell in the future. It's like you build an engine and later you put this engine into a chassis, right?
I see. And you've also developed another synthetic system called the TACO pathway. Can you tell us about that?
Now it's getting confusing, all these different names and solutions. Yeah, absolutely right. So the TACO pathway is also an artificial synthetic pathway. I want to give you one difference. Let's say the catch cycle is a complete new engine we built. Let's say an electrical car, we need a new engine, right? Let's take a normal car, a diesel engine, you want to tune this engine. And TACO pathway is more tuning existing photosynthesis with new solutions. And the catch cycle is building a complete new engine that drives in a different way. And so these are the two ways of trying to improve photosynthesis on a mid and maybe on a long-term scale. And arguably, the TACO pathway is much faster to realize compared to the catch cycle, but it's not as efficient.
There's a lot of different layers to your research. Where did it go from there after you discovered that one?
I think science is non-plannable, but you can have visions where to go, right? And sometimes you face a challenge you might be able to solve or not to solve within the next 10 years. So I would say we have now these operating systems, like you just mentioned, TACO pathway or the catch cycle. One of the big challenges now to put those systems back into a cell-like environment. This could be natural cell, as I said, a plant, or it could be an artificial cell. I think these are currently the most exciting experiments in our lab. So will those systems also work inside of a host, of a living or artificial host?
Is that a step that's next then, to try it in an artificial host?
Yeah. And the reason why we also build so many different solutions is, they might actually work outside of the cell. They might work in the lab, just isolated, but they might not work inside of the cell. You basically develop maybe 5 or 10 solutions, and of these 5 or 10 solutions, maybe only one will be functional inside of a cell. And so this will be a lot of testing, a lot of tuning, a lot of trying to engineer cells to accept these new operating systems. And this is where it also becomes really difficult to predict how cells will react to this new software and these new solutions.
If you're like me, then you're curious about the future and what that will look like for our children and our children's children. A great place to feed my curiosity is at the Curious Future Insight Conference that happens every other year. I've already got my tickets to head to Mainz, Germany on the 10th and 11th of July for this year's edition. Over the 2 days, academic and industry leaders will come together to share their knowledge and their latest innovations. They will talk about the problems we're encountering on a global scale. But this is not a conference that focuses on everything going wrong. Quite the opposite. The Future Insight Conference is a really positive and uplifting place to be because the speakers have been working for years on solutions. From major players like Merck to startups only a few months old, the lineup of keynotes and panels really show the seniority in each industry. And the best part is that everyone is talking about what they're doing to make a difference in the world. This year, among many others, they have the CEO of BioNTech, Ugur Sahin, the founder of Boston Dynamics, Mark Rybert, and also the Nobel Prize winner and professor Stephen Chu. It's a place where you can connect with like-minded individuals in academia and industry, take part in workshops like the Microplastics Hackathon, and you may even be interested in entering yourself or your company into one of the many competitions they have running annually. They have the Nature Spin-off Prize, Science and Shorts Prize, and the Future Insight Prize is the creme de la creme, awarding €500,000 as a helpful research grant. If you want to find out more about the event and grab your tickets, head over to curiousfutureinsight.org to find out more information. I'll also put a link to the page in the show notes. And if you do come and you see me there, please don't be shy and say hi. It will be such a pleasure to connect with you all. So how do you actually plan to go about implementing these pathways into a carbon capturing model? What would that model actually look like?
So it's two things that you need. You basically need the idea and the software, or this kind of catch cycles, taco pathways, however you call it. And at the same time, you need tools to engineer the organisms to bring these complex pathways in. And I think what we currently are trying to do is establish new technologies to radically reprogram organisms. And that is really automated, high throughput ways to, for instance, modify and manipulate the chloroplast. And that is where we invest a lot. And hopefully we manage to really get those systems or parts of the system inside of a chloroplast to see what the effects would be.
And so what is the next milestone that you hope to achieve with your research?
If I could dream, I would like to see the catch cycle operating inside of a living cell. Because if you think about it, cells are not just bags of enzymes or small envelopes that you can put stuff into it. They have billions of years of history. It's almost like you would have an engine, right, or car, and then you try to put a complete new engine in. So you have to really rewire a lot of things. A lot of things are interconnected, right? This is what living systems are, highly complex things. And you cannot just change a part. You need to take everything into account. And I think what we have to learn is how to tweak those systems and how to generate incentives that they accept this new software. And so my dream would be to get parts of the catch cycle functional, parts of the taco pathway functional inside of living systems, and then let evolution take over and see what the effects are. And hopefully the system is convinced that the new way to fix carbon is much better. And this would be fantastic.
I know research takes so long as well. So how long do you think it is before you start seeing some of these developments?
Okay, that is basically a teaser for my talk. So we do have some really good experiments. And I would like to share also what we've achieved in the last 2 years, also through support from the Future Insight Prize, right? So we actually have established a way how to manipulate the chloroplast at high throughput, and we've actually put in small pathways, and they seem to work. So we're very excited to now prototype and enlarge our screen capabilities. And I think that is what I would like to share with you when I give my presentation.
So that's a very big teaser. We have to tune in to the Future Insight Conference to hear more. And for those people who are listening to this after the Future Insight Conference, I think there might be information available on their website. Sometimes they'll show some of the talks then afterwards virtually. So fingers crossed you can hear after that. Well, thank you so much for explaining all of this to us. Are there any tips that you would give our listeners to reduce their own CO2 emissions?
Well, first, I think you should just get aware where you basically emit CO2, right? You should really consider how much you travel. You should also consider how you travel, right? How you commute every day, right? I think it's the small steps that are really important, right? Buying fruits, do they need to fly across the ocean, right? Do we eat seasonal? All of these small steps matter at the end of the day. And it's not the governments, right? It's us, each individual, that can make a difference in a decision. And I think getting aware of what your footprint is one of the biggest achievements. And then we can work together as a society to try to improve. And I think this would be fantastic.
And where can people keep up to date with what you're doing?
Well, of course, you can always come to the Curious Insight Conference. Curiosity is the first step. I think what we're also doing is reaching out to the society, and we actually have developed, let's say, programs for schools where we work with school kids, because those are the next generation scientists, but also the people to be most affected by the global change and the climate change. And I think it's really important to tell them that science has solutions. Some solutions take time. And certain technologies also come with certain risks. We are talking, for instance, about genetically modified food or genetically modified organisms, but we can balance if they are of benefit for the climate, if they are safe, why should we not use them? And I think that's also part of education, is to empower people to make deliberate decisions and to tell them there is a way to overcome all these challenges, and you can actually be positive into the future. And thinking beyond, let's say, the current limitations is maybe a way to find new solutions. I think we human beings have shown this several times, that if we wrap up and get ourselves together, we can find a new way to treat cancer, we can fly to the moon, and we can save the climate.
And so what is it you're actually doing with the schools? Just giving them talks, or kind of starting initiatives with them?
It's actually fantastic. So the high school examination, the high school textbooks have actually put in our catch cycle as an example what science can achieve. And this is fantastic. So what we now empower them is to build their own pathways. We've designed a small memory, a small game you can play in school. You can design your own pathway, you can put it together, and you can calculate how efficient it is. And the kids just love it, right? And so we're hoping to roll it out now to all the schools in Germany, maybe even internationally. It's a very nice way to get into the science, but also very interactive. And it shows the creativity that you need to have as a scientist, and also the communication and working the team. So I think it touches on many points that I like to do when I'm doing science.
Yes, definitely. And I look forward to hearing more from you at the Future Insight conference as well. Just for our listeners, if you are hearing this and you want to join on the 10th and 11th of July, you can do that virtually if you're not able to get to Mainz, Germany. So just go to curiousfutureinsight.org for more information on how to register. Do you have a website where people can follow what you're doing at the Max Planck Institute?
I do have a website. I can't memorize the URL, but you'll find it there. Just Google Tobias Erb, Max Planck Society, and right there you are. And it's actually a lot of content that's also for the non-scientists, a couple of explanation videos. So I think we take it seriously. And you can follow me on Twitter or X. How's it called now? It's called hashtag or handle Erb Labs.
Fantastic. Thank you so much. We'll also put all those links in the show notes as well so that people can find them very easily, along with the one for the Curious Future Insight conference that's happening on the 10th and 11th of July. I'd love to also mention our Instagram account, BeCurious_podcast. That's where you can go to find out more information about the show, to see all of the guests that we have on, and also to find out about the giveaways that we have. Many of our guests have gifted us something, and you can enter our competitions via Instagram. So just go to BeCurious_podcast to find out more. I'm your host, Louise Houghton, and until next time, thank you so much to Toby, and stay curious, guys.